Hello, everybody, and welcome to the Microsoft Data and AI South Florida user group. My name is Adriano, your host, and today we have a very special presentation, as always, here bringing to you so you can expand your knowledge. Now, before we get started, let us know where are you located. Use the live chat window and enter your location. So I'm located in South Florida, and soon we will hear about what is Kevin's location. But in the meantime, where are you located? Also, the live chat will be used to enter your questions. So if you have a question during the presentation, use the live chat. If the presentation has completed and you're watching it on demand, use the comment section below to enter your questions there. So without further ado, what is next here is today's presentation, which is going to be getting beyond the basics with Azure Machine Learning with Kevin Feasel doing the presentation today. A very exciting presentation to get you all started or going beyond the basics of Azure Machine Learning. So now, folks, without further ado, I bring you Kevin. Good afternoon, Kevin.
Hello. Welcome, everybody.
Hello, and thanks for being here, Kevin, as well as for everyone else watching us here. So, Kevin, tell us where are you located at?
I am out of Durham, North Carolina.
All right. And can you tell us a bit about you there?
Sure. My opening shtick is that I'm a Microsoft Data Platform MVP out of Durham. I have a little consulting work that I do, but also by day, I'm a data scientist working at a company that builds large boats.
Excellent. And can you tell us a little bit about today's presentation?
Sure. What we're going to talk about over the course of the next, I think it's 7 hours that I've got, but we're going to talk a little bit about the constructs of writing code first machine learning. We'll see how we can use Azure Machine Learning, not in the drag and drop, click, click, click type of scenario, but more of a practical, productionalizable scenario with Python code in this case.
Excellent. A very interesting and exciting topic here. So, without further ado, let's get started. Let me get your slide right here. All right. And folks, remember, use the live chat to enter your questions. And as always, remember to like, subscribe, and also register to the user group. All the information is on the description section below. And thank you, Masood, from Chapel Hill, nearby your area, isn't it, Kevin?
Oh, yeah. No, I know Masood. Howdy, Masood.
There we go. There we go. All right. It's all you now, Kevin. Thank you.
All right. Thank you kindly. So, as mentioned, we're going to be talking a bit about Azure Machine Learning today. I've already done my introduction. I've done my spiel, except for one tiny part, and that is curated SQL, where every day I try to find and link to 5 to 10 interesting posts on topics all across the data platform space. That's curatedsql.com. We are going to talk about a few things today. And by the way, if you have questions, if you have anything that uh, you want to bring to mind, drop it in chat. I do see chat, but Adriano will be able to moderate everything as well so that this is a very classy establishment and I don't just jump the gun on responding to chat. We'll have plenty of time for questions. Just drop them in whenever. But I will briefly talk about Azure Machine Learning, especially because I expect, having given this talk a few times before, a large percentage of people who are watching it haven't really worked with AML before. And as a result, I'll give you an idea of the nickel tour of the product. Then we're going to dive into code first machine learning. And that's the whole premise of today's presentation. How do I write code, deploy code, work with code versus designer interfaces versus a lot of graphics heavy SQL Server integration services like lines connecting to boxes. We'll talk a bit about model registration, talk a little bit about ML flow, talk a bit about the pipeline metaphor that works with machine learning, and I will very briefly touch on machine learning operations. However, I have an entire talk dedicated to that. This is kind of a talk 2 in a 3 talk series, and I'll give you links on where I've got videos for all of this stuff. So, very briefly, we are going to see how we can work with notebooks within Azure Machine Learning. But notebooks are a starting point, not an ending point. As a result, we're going to start writing Python. We're going to go through a fair amount of code, understand what's going on, how it works, build out not only how we train a model, but how we can perform scoring using that model. We will see what this looks like in the UI as the training pipelines or the scoring pipelines execute. And we'll get some information that we pull back and get to see some of the results. So let's start off with a primer on Azure Machine Learning. This is Microsoft's primary offering for machine learning in the cloud. This is kind of, sort of tied in just a little bit with Azure OpenAI and the generative AI push. There are components that find themselves somewhere straddling between AI Studio and Azure Machine Learning, but we're not really going to talk about that today. This is more of, I'll call it classical machine learning techniques, which can include neural networks, but stuff that's not generative AI, basically. That's the main topic today. Within Azure ML, we have a series of components. The first one is data stores. This is just a connection of, where does my data live? Oh, this data is in an Azure SQL database. This one's in Azure database for Postgres. This is in a storage blob. So data lake storage or just a regular Azure blob storage. These are pointers. Data sets then contain the actual data that we're using to train models. A data set, you can upload a file locally, or you can use a data store to say, go find this data from the data store, and then we're going to track that information in Azure Machine Learning as a data set. We do need something to run on. We need compute. And AML has several different options for compute. The one that we're going to spend a lot of time working with, or one of the two that we'll spend a lot of time working with, is compute instances. Think of a compute instance as a data science virtual machine that's available to you in Azure. They have a lot of libraries pre-installed. You can install your own libraries on it. You can build out your own scripts to generate a new compute instance. And the idea would be that on your team, every person would have their own compute instance. You can see in this demo example that I have mine stopped. That way I don't have to pay for it 24/7. So we can start and stop these VMs just like any other virtual machine in Azure, and we're not paying for the compute when it's off. A compute cluster is a little bit different. A compute cluster is a set of machines. Now, that could be one machine technically, but we can have a cluster that's bigger, 2, 3, 4, 8, 12 machines. And these machines usually are going to be a bit more powerful. This is kind of in the metaphor of, if your compute instance is a data science virtual machine, or if it's a laptop for the developer or for the data scientist, the compute cluster is your big iron. This is your server. Uh, this is where you're going to deploy out jobs for training and for scoring. So you may have multiple larger machines to be able to work on a problem. The compute cluster will automatically disengage after a certain amount of time. So you don't have to remember to start and stop it. It'll just shut itself off after a certain amount of time idle. When you're working with Azure Machine Learning, the starting point, I do recommend starting with the designer, because this gives you an idea of how the metaphor of pipelines works in the machine learning world, and specifically in the Azure Machine Learning world. And it's a drag and drop interface. So it's easy for somebody to get started, get a brief understanding of what components are available, what options do you have, and then we can build on top of that. So the designer options are a subset of all of the things that you can do in Azure Machine Learning, but it's a pretty decent start. When you're running, regardless of whether it's from the designer or if you're running code first, we have this idea of experiments. An experiment, just like going back to science class, this is going to allow you to try things out in a controlled manner. We want to keep track of different runs of the experiments where we might change a parameter, we might change some settings, we may try a different algorithm, we might try different subsets of data or splitting the data a different way. Regardless of what factors, what variables we're tweaking with each run of the experiment, our goal is to gain some information, gain some insight. And the experiment is just a bundle. It's a call it a top level container for all of these different runs. And the runs contain a series of measures where we might track the duration. We might track things like how accurate was the model, how, if it's classification, we may look at precision and recall or positive and negative predictive value and all of these other attributes. So we're able to track these measures, store these measures on a per run basis, and then I can compare the different runs and say, oh, well, when I tried just a regular decision tree, I tried CART, I got this accuracy and this precision. When I tried a random forest with this maximum depth and this many trees, I got an increase in accuracy. But then when I tried gradient boosted decision trees, I got something different. And so it gives us an opportunity to experiment. Now, the primary purpose of our experimentation in Azure Machine Learning is really to create a model. We want to have our trained model that will be available for use, for scoring, for prediction, uh, and we're going to be able to store them in the Azure Machine Learning model store. Then we can have an endpoint. Now, that endpoint is how we can connect and talk to the model. Azure Machine Learning will do a lot of the back end plumbing that's necessary to convert your model binary into something that an end user can call. There's a little bit of work that we have to do, but it's a small amount compared to the whole effort of standing up servers and uh, exposing ports and setting up network configurations and all of that stuff that a data scientist doesn't really know that well or want to do. So the endpoint, that's our place where we can go send in data, score, get results back. There is another type of compute called the inference cluster, and this is an easy method for hosting endpoints, either for real time or batch scoring. And that is the nickel core. We could absolutely dig into each one of these components further, but we don't really need to for the course of today's understanding. I will point out some interesting pieces, point out some of the things that we'll need to know in the Azure portal and specifically in the Azure Machine Learning Studio as we go along. But I won't belabor that too much because we have a lot that we want to talk about with code first programming. So the idea here, Azure Machine Learning's designer, it works well enough if you're trying to learn the basics of a machine learning project. But you're probably going to want to write code if you are getting serious about training a machine learning model and using it in Azure ML. You're going to want to write your own code. And there are a couple of methods available for writing code. And I will talk to and show off both of these. The first one is we can use Jupyter notebooks. You can execute code in a notebook, and we'll talk about why you might want to do that. And then you can execute code from machines. Now, I'll show you using Visual Studio Code in today's demos. You don't have to use VS Code. I just find that it's the most convenient mechanism for this because there are some good extensions built in. There's really good Python support, and it ties in well with some of the console level tools that we'll need for the presentation and for deploying a model. When it comes to notebooks, Azure ML on those compute instances has Jupyter Notebook support built in, and there is a pretty nice interface for running notebooks from the Azure ML Studio against your compute instance. So you don't have to learn how to start up a Jupyter Notebook and hosting ports and trying to figure out all of that nonsense. It's baked into the interface. There is also support for a Python SDK. So Azure ML has the Python SDK v2. It's important to note there was a v1. The v1 SDK was a bit different. There was an SDK for R, there was an SDK for Python. In v2, there is only a Python SDK. For all other languages, if you're writing C# or F# code, you're writing R or something else, Java, you can use the Azure CLI, AZ-CLI. There is an ML extension that you would install, and it has the same capabilities as the Python SDK. So if you wanted to write code in R, you can write code in R. It is, I'd call it, there's a minor increase in difficulty level for getting this to work, but not a huge one. Now the SDK has its benefits. It's a lot easier to write code against, I think, than writing the code in R or writing the code in C# or even writing the code in Python and then using AZ-CLI to perform all of your deployment actions. But regardless, we are going to use the SDK, the V2 SDK, and I'll show you how you can tell the difference between those two. And for every other language, use AZ-CLI. So when do we use which? We are going to use notebooks, exploratory data analysis, rapid code development. The idea here is this is your opportunity to write code that may not be production worthy, but the intent is we're going to get some answers quickly. I can display my results. I can quickly build graphs. I can try, revert, until I'm satisfied with my results. That's where a notebook shines. Now, for the SDK or the CLI experience, the idea here is we're writing code and we're going to have to write this code, get it working, and then we can deploy, we can automate, we can log results. This is, I think that you can absolutely start in a notebook experience and then convert that into code. And that turns out to work reasonably well. Or you can just start in the code experience if you have a better feeling of the code that you want to write. So I do recommend for major push, uh, use the SDK or the CLI experience, write code first. Don't rely on notebooks for production. Work with notebooks as you're exploring and experimenting, and then use the SDK for real work with real and scare quotes. So with that, let's check out the Azure ML Studio. I'm going to pop that full screen and give you a quick overview of things. I am currently down here in the compute tab, and compute instances, I've got the CS compute started. It's been running. Note that I do have an idle shutdown of 1 hour, which means I better get using this pretty quickly. And there are some applications that are pre-installed on it, like Jupyter Notebooks, Jupyter Lab. You can run Visual Studio Code, the web version, from or against your compute instance. I'm also going to show off some data that we've got. The data that I will use today is Chicago parking tickets data. So this data comes from a database that Daniel Hoopmacher put together. And I have praised Daniel for doing this literally dozens of times. And I'm going to praise him yet again because he's put together this amazing data set of basically every parking ticket from the city of Chicago over about an 18-year period. And he's tracked quite a few pieces of information about it. I grabbed his database. It's a SQL Server database backup that you can restore to your SQL Server instance. And I wrote a query to extract a lot of this data out. I took out a sample, as I recall, is about 1 million of these records. Tells you how many tickets the city of Chicago writes. And there's a good amount of information on here, 19 total columns with a lot of information spanning from when the date happened, so when the ticket was written, and locations, information, information about the population, demographic information, things like percentage of people in that area without a diploma, or the neighborhood, the ward, the zip code, which police station or which district are they in? Was this a passenger vehicle or commercial vehicle? Was it a uh, emergency services vehicle? Actually, there are a few tickets of that type. Which state the license plate associated with? Obviously, Illinois is going to be very popular there, but Illinois is not the only state that people get tickets in Chicago, and so on. So, quite a few columns. What I want to understand is this column at the end where I created this myself, and it's called payment is outstanding. The idea of this column is this is a one if the person who received the ticket has not fully paid the ticket off. So, like this case, somebody got a ticket in the year 2000 and they just never paid that thing. By contrast, it is going to be a zero if person paid the ticket, if court threw it out, or there were other mitigating circumstances that made it so that they didn't need to pay the ticket. What I want to predict is under what circumstances are we expecting someone not to pay a ticket? And that's going to be our goal for today is to create a model that hopefully understands and helps us find the factors that relate to this. All right, let's go here into notebooks. And I told you a little bit about the data, but let's really dig in. And I've got here a notebook, Chicago parking ticket analysis. Now let me minimize that. I'm going to shrink size just one step. We're going to note that I have this compute instance running and I'm using a Python 3.10 kernel. So we can see there are some older kernels on here for this compute instance because I'm going to have to delete and recreate it at some point. But for now, I'm okay with Python 3.10. And I have other possible compute instances. I can even run it serverless if I have a reason to do that, which I don't here. Next, we are going to kick off some scripts from Azure ML.core. If you ever see this statement in your Python code, this is actually the SDK v1. I'll show you what SDK v2 looks like when we get into our code, but we're going to bring in some items from Azure ML Core, and then I'm creating a workspace from configuration. What that means is there's a config file, there's a JSON file that has information on my subscription, my resource group, and my Azure ML workspace. I need that information in order to be able to connect to different resources. And by putting it in a config file for me, all I have to do is call this workspace from config, and I don't have to think about it any further. Next up, I'm going to get data from the Chicago parking tickets data set. So we saw that data set, and then I'm going to convert it to a pandas data frame. Now, how many records do I have in here? As mentioned, I have 1 million records. Next, let's take a quick peek at some of the data. We did already, I kind of scrolled over and scanned a little bit of it, so I won't belabor that point here. But we do see that information on each of these records. And there's a mixture of data types. I've got date times, I've got strings, I've got numbers, and there's one label. The label is, oh, there we go. The label, payment is outstanding, represents the thing that I want to understand or predict or uh, infer based on the rest of this data. So I have a whole set of features, the information that I expect will help me understand my label. and I have the label itself, the thing that we're actually aiming to predict here. Within each of these features, we're going to have a set of values. So this is the unique set of police districts. So you can see that police district does actually show up as a floating point number, except that all of these are integers except for not a number. So there apparently is some data that is missing police district. And the fact that there's missing data has tricked pandas into thinking that, oh, well, this is really a float. It's really a floating point. So um, I may want to think about that. If I think police district matters a lot in whether you're going to pay your tickets or not, then I have to think about how I can deal with these missing police districts. But I don't want to manually go through each one of these columns to get how many unique values there are. To that extent, I can use a pandas function number of unique values and apply that to every column in the data frame. So for issued date, there are 914,054 unique issued dates, which means roughly 80,000 of these tickets were issued at the same time as some other ticket. Again, Chicago's a big city. There's a lot of tickets that they write. But for the rest of this, for the most part, there aren't a lot of values. 77 communities, that's a little bit big. Look at 98 neighborhoods. So 98 neighborhoods across the city of Chicago, 13 sectors, 9 sides. You can see that the hardship index, per capita income, both of those appear to be based on the community. Percent unemployed and percent without diplomas, percent of households below poverty. These are also based on community, but it turns out that there's some overlap where two communities will have the same value. And as I looked through this, most of this data I would classify as categorical in nature. Where categorical, the way I like to explain that very simply is, could you reasonably imagine all of the values showing up in a drop down list? Like zip code. Could I reasonably imagine the set of zip codes for the city of Chicago in a drop down list? The answer is it may be a little weird, but yeah, I could. There's 59 of them. Um, but some of these a little bit bigger, like violation ID, unit ID, tracked. There are nearly 800 tracked. That is getting to be a bit big for what I would normally consider categorical data. Okay, couple things I want to point out. License plates. Actually, I should scroll back up to how many license plate states there are. And there are 64, whereas we know there are only 57 states. So the question is, what gives? It turns out we have here Illinois, Indiana, Michigan, Wisconsin, Iowa, Ohio, all states near Illinois. And then we start getting to other big states where you probably have rental cars with different tags. And if I scroll down further and further, we start getting into states that are not actual states. We'll get into things like New Brunswick or Alberta, Quebec, etc. So these are also collecting Canadian provinces. They're collecting uh, what we normally would not consider states, at least not until we take them. Um, but plate types. So we're gonna have to deal with what we think of as states. Also, one other thing that I need to mention about states is look at Illinois. 914,000 of these plates are from Illinois. The next closest is 17,000. This is very, very heavily skewed toward Illinois and makes me think if I want to do an analysis at the state level, once I get past a few of these, I probably don't have enough good information to draw any conclusions. So, as a spoiler, what we're going to do is we're going to say in state, out of country. And that'll at least give me larger bundles of data so that I can possibly discern something from the aggregate versus I've got literally one ticket in my data set from Newfoundland. I'm not going to draw any conclusions from that. Similar story with passenger type with plate types. 871,000 are passenger vehicles, 51,000 are commercial trucks, and there are a series of other vehicle types that you've only got 800 tickets in this entire million row data set. I'm not gonna probably draw good conclusions from it. So I'm gonna bundle most of these back together and say passenger vehicles versus basically everything else. When it comes to payment is outstanding, we can filter and say, tell me the ones where payment is outstanding, tell me the ones where payment is not outstanding, and you can eyeball it. You're not going to draw any real conclusions just from looking at a few records like that. Unfortunately, it'd be cool if we could, but then this would be a trivial data set to work with. So instead, let's do a little bit of correlation analysis. And what we're doing is I can take numeric features and see how well they correlate. Correlation being that if the value of one goes up, how does the value of the other one look? If it also goes up, we have a positive correlation. If the other value goes down, we have a negative correlation. If there doesn't seem to be a consistent pattern, sometimes goes up, sometimes down, we have effectively no correlation. So, give you a practical example hardship index versus per capita income. We see that there is a negative 0.87 correlation, where 1.0 is perfect positive correlation, negative 1, perfect negative correlation. One factor goes down, other factor goes down. Or excuse me, one factor goes up, other factor goes down. That's perfect negative every single time. Almost every time per capita income for an area is lower, the hardship index is higher. So hardship index up means less income or higher unemployment or higher percentage of people missing diplomas or higher percentage of people uh, below the poverty level. Those features are all very closely tied together. And there may be some difficulty in separating these things out if we want to help understand the factors that drive whether somebody pays their ticket. So we might have to think about, well, do we want to keep all of these features in with hardship index? Or do we keep hardship index, drop some of these because they're just too closely tied together? By contrast, if you look at zip code, hardship index and zip code has almost a zero correlation. To understand the reason behind this, zip code here right now is basically uh, think of it as alphabetical order or numerical order. So there, you could say within zip codes you have certain hardship indexes, and that some of these will have a higher hardship index than others. But just because you moved from like zip code 43123 to 43124 doesn't mean your hardship index will definitely move in a single direction. That's the idea here. If you think about town, a big town, there are going to be parts of town that are bad, parts of town that are good, and it's not like all the bad parts all cluster in the same area, and then all of the good parts have uh, zip codes that are totally different. So not a good correlation between these. And also, payment is outstanding. Hardship index has a small positive correlation. If somebody wrote the ticket, police officer wrote the ticket in that particular district with a high hardship index, you are slightly more likely to not pay the ticket. And what we're looking for is how closely do any of these features correlate with payment is outstanding? We want big positive or big negative. And it turns out none of our features are particularly well correlative with payment is outstanding. Again, that's okay. What it tells us is this is not going to be a trivial solution. Also, we can perform some feature engineering. We can do things like I want to take the issued date, which is actually a date and a time. If I scroll back up, this is a date and a time. Well, the exact date and time that you wrote a ticket has very little informative value from a prediction of will you pay that ticket. We can theorize that maybe people who get tickets late at night might be more or less willing to pay than people who get tickets at rush hour. Uh, but the exact time, like the fact that this was 2014, August 21st at 9:31 a.m. Central Time, I can't draw conclusions from that exact point in time. So what I can do is try grabbing the year and the month and see, is there a correlation with year? Maybe as the tickets are older, they're less likely to get paid, or if they're newer, they're more likely to be paid. And the month, maybe certain months of the year, people are more likely to skip on paying tickets. If I scroll over and look at this, basically for year, I've got month, and then payment is outstanding now becomes this feature that's third from the end. So if I scroll down, there is a minor negative correlation with year. Older tickets, a little bit less likely to get paid. Um, that's kind of interesting. But month of the year doesn't seem to have a factor. So we don't really have to think about month of year. Okay. Some final cleanup. Let me look for missing data. So do I have any missing values? I look at this, I see there are missing tracts, there are missing police districts, plate types, license plate states. And we're going to have to think about how can we deal with this data. Ultimately, what I've done through this notebook is explored what the data looks like, tried to understand a little bit about some of the relationships in the data, and take my plan of action. So I'm going to find and replace missing values for police district. I'm going to create a year feature. I'll create a time block during the day. I didn't really dig into it, but I'm going to explore that in my code. I'm going to look at the license plate origin that's based on the state. So I won't take the state itself. I'm going to bundle things together so that not everything is Illinois or a state that has a few records. And the vehicle type, similar idea. We'll remove the hardship index because it correlates too closely with a whole lot of different features. And we'll also remove the census tract because there's a good amount of overlap with everything else. And it looks like, there we go. So we're going to take care of that. We're going to code some categorical features. We'll do a classification analysis. That's the plan of action. With that plan of action in place, let's come back here and talk about running some code. So I can execute notebooks and I can execute code in my local machine using the Azure Machine Learning extension for Visual Studio Code. So I can, from there, connect to a compute instance, execute against that compute instance, and do some work. The extension is a direct interface for your Azure Machine Learning workspace. And we can see in here, I have my data sets and experiments. I've got models. I've got endpoints in my compute instances, some compute clusters, etc. So many of the things that we saw in the Azure Machine Learning Studio, I can also get locally from VS Code. And actually, one thing I should point out that's on the slide, I can also run my uh, code as a local compute instance if I have Docker installed. Ultimately, what Azure Machine Learning is doing is it's taking our code and creating a Docker container off of that code, deploying out that image to a container registry, Azure Container Registry, and then instantiating the image to execute locally. We could do the same thing on our own machines if you have Docker installed on that machine. If not, run it on the compute instance, run it on the compute cluster. Before we really get into running, I do want to talk just a little bit about the flow of things, how code maintenance works, how code operations work. Then we'll get into pipelines. Then we're going to dig into code itself. MLflow is a library that uh, came out of Apache Spark, came from Databricks, and its purpose is to manage the machine learning development lifecycle. So specifically, MLflow allows a data scientist to train models, to register those models, and then deploy them out to a server and manage updates. All of that sounds really neat. And it is most heavily used in Databricks because they were the progenitor. But you can use it with Azure Machine Learning. And also, even if you don't use MLflow itself, Azure Machine Learning's interfaces definitely grew out of ideas from MLflow. And as we talk about it, I'll show you how. There are 4 total products that make up MLflow. The first one is the tracking product. This is what allows a data scientist to work with experiments. For every run in an experiment, we can log some parameters. We can track what versions of libraries we're using. We can track the evaluation metrics, even take generated output files. I can create images and store them. I could create PDFs and store them. And I get all these things when I'm training my machine learning model. With MLflow tracking, I can review and audit those prior executions, review the artifacts that we generate, and see what the results look like. With MLflow projects, this is a way of packaging up code that allows for a consistent deployment experience. I have a few different options. I can package these up as Conda packages. I can create a Docker file and create a Docker image, or I can just push this code directly onto a system. When it comes to models, MLflow has a standardized format for model packaging, and they can take models from a variety of libraries. Scikit-learn, PyTorch, TensorFlow, Onyx. There's a whole series of model types that it supports, and it will serialize the outputs in a particular way so that we can deserialize this model and work with it later, regardless of whether it came from scikit-learn or if it was an Onyx model or if we trained a generative adversarial network in PyTorch. And we're going to store these models in a model registry. What we can do from there is after your data scientist says, yep, I'm happy with this model, let me put it in the registry. Operations staff can deploy the model from the registry. You can either serve it as a REST API or has an endpoint where we can perform batch inference. Now, as I've explained all of this, if you're already using MLflow, maybe you've got Databricks set up, you're familiar with it, you can use this with Azure ML. So you could have an MLflow server, and Azure ML can communicate with it, send information to it, and display information from it. But if you don't, the model registration and other capabilities that are in Azure Machine Learning, they emulate the key capabilities of MLflow because we have experiments. Well, that's essentially what we talked about with MLflow tracking. They're very similar ideas. For every run of the experiment, we're able to track details of the metrics that we've logged. We can save artifacts. We can see what the code was, see the parameters that we passed in. And then for projects and pipelines, if you're using MLflow projects and you're packaging up your code, well, you can execute that code on Azure ML Compute. Now, in Azure ML, there is no direct correlation to projects. There is this notion of pipelines that I'm going to talk about in the next section that is kind of the closest thing to what we've got. For the model registry and model deployment, well, I can register and store those models in the ML and the Azure ML models section. I have different models, I have different versions of the models, and uh, I get artifacts like here's a pickle file, or here are the relevant weights associated with this neural network. Any kind of helper files that I need, anything that will assist me along the way. My data sets, I can even track how I trained this model, which can be very useful for after the fact analysis. If I have an auditor come in and ask, well, what data did you train this against? I can note here was the data set that we used because I've registered the data set in Azure ML. I've got a version of it, and here's my trained model. So I can review and say, yes, this was the data that we trained it on. You can see that there's no specific personal information, that there's no demographic information that we might not be allowed to use, that kind of thing. When it comes time to deploy, well, your operations people can deploy this very easily. There's a button, so push a button, and we can deploy out to a real-time endpoint, to web services. This screenshot is just a little bit old, but the idea is still the same. We're able to deploy our model out, make it available either as a batch endpoint for inference or as a REST API that we can execute code against. Sounds very similar to what we're doing in ML Flow. So you can see the exchange of ideas between those two products. I mentioned the idea of pipelines. Let's talk pipelines. Azure Machine Learning, the entire working concept is pipelines. We're going to perform data cleansing, easy for me to say, data transformation. We're training models, we're scoring models, we're performing inference, we're evaluating how the model did. These are all different steps in our pipelines. And so I can then have my trained model, deploy it out, perform inference. Well, later on, I might generate predictions or perform scoring against data that I've got. And I could even go back and evaluate that later on. As a quick reminder, we have that designer. That designer allows us to create drag and drop components, and this is a pipeline. You can even see the visual metaphor right here because I've got my data source and I'm flowing it through a series of components, and maybe I have other things in here that feed in, but you can see this visual flow of, imagine it, water through a pipe. This is extremely common in Azure ML as the constant metaphor that we're working with. And there are good reasons for that because um, we can control deployment. We can control and say, I need to, if I go back to the neural network example, I may need to perform fine tuning of an existing neural network model. And that fine tuning, I'm going to need GPU compute. But GPUs are expensive, especially in Azure. But I don't want to have all of my other steps that don't take advantage of GPUs run on that same hardware. I could run it on less expensive CPU only compute and save a lot of money if I have a large model and a large process. So if I have a pipeline, step one of the pipeline might be certain data cleanup. I don't need GPUs for that. Uh, Feature engineering, feature selection, etc. But then fine tuning. Now I need a GPU. But then once I fine tune the model, I may not need a GPU after that. I might be able to do CPU based scoring. So I might have certain steps along the way where I have more expensive hardware and less expensive hardware. I can reuse components between pipelines. Let's say that I've got a data science team and I have several products that I've built out. I might have a consistent mechanism for fixing misspellings or for applying terminology that's consistent within the organization. And I may want to reuse those components. Well, if I didn't have an independent components that I could plug in and interact with, that gets a lot harder. Whereas I may have some utilities files that I can bring in. Like, here's a Python package that I can bring in and say, this type of component does a specific bit of work. I can collaborate with other people. If I have one person on the team who is focusing on data cleansing, one person who's focusing on fine tuning, one person who's focusing on operationalization, we can all work concurrently without really stepping on each other's toes because each of those steps is independent. In order to execute any of this code, I'm going to need Python. I'm going to need the Azure ML SDK v2 for Python. I do have a note here that it is probably a little bit easier to install Anaconda distribution of Python. However, given the licensing changes that have happened in Anaconda, I know that there are people who will say, I don't think I want to do that. You can absolutely run this with bog standard Python. In fact, my demo, I will use regular Python, not Anaconda distribution. Speaking of demo, let's get in here. I am in Visual Studio Code. We have our notebook. I could have run the notebook locally, but I prefer to run it in the compute instance. Instead, I'm going to get into this pipeline folder, and we have a fair amount of stuff to go through. So I have a deploy train.py. This file is the training script. I will use this script actually to execute my code. And while I'm talking about this, how about I need to go into my pipeline folder and Python deploy train.py. We're going to find out if this works. So fingers are crossed. While it's going on, let me talk about what's going on. First thing that's happening is it's reading in Azure ML a config.json file. I will not open this up because it does have my subscription ID. It does have my ML services workspace and my resource group. So let's hide that again so I don't accidentally show it. In our code, I have this azure.ai.ml. This is the Azure ML SDK v2. If you see Azure ML.core, that's v1. Azure.ai.ml is v2. So you can see that I've got quite a few things that I've brought in, quite a few import statements. And it looks like it may have succeeded. That's good. That's very good news. We'll give it a moment. In my code, I'm going to set my workspace, CS Azure ML. I'm going to set a compute cluster called CPU cluster. If I pop back into Azure Machine Learning and I go over to compute and I check out compute clusters, I can see that I do in fact have a CPU cluster. And by the way, I have one active run. So that's looking okay. My job, I've got step replace missing values that was queued today. So that seems reasonable. And if I look at these jobs, I've got this Chicago parking tickets code first train pipeline. I'm just gonna leave this here for now. The gray bar here means we're waiting for a server to spin up, which means I've got plenty of time to talk through the code. So I'm looking for this compute cluster, CPU cluster, and for local run, I'm going to use I could use a default Azure credential, but because I've deployed this out, I'm going to use my credential that is associated with the compute instance. So here I'm logged in through the Azure CLI to my subscription, my workspace, etc. And that's why I'm able to get my workspace on line 35. Then I'm looking for this compute cluster. If I have the compute cluster, I'm going to print that I already have a compute cluster and we'll use it as is. And in fact, if I were to scroll up all the way to the top, there we go. I'm near the top. You already have a compute cluster named CPU cluster. We'll reuse as is. Very nice. Except if I didn't have one, then I would create a new compute target and I would need to create an AML compute. So the type is of Azure Machine Learning compute instance. Size, I'm using a pretty small and old machine because it's cheap. Minimum of 0 instances, maximum of 4 instances. These are compute clusters. I misspoke and said compute instance. So this is the compute cluster that basically says you can turn off. If nobody's using you, minimum instances is 0. Go ahead and turn off. Don't make me pay money for something I'm not using. And scale it down after 3 minutes. So if I'm not running another job within 3 minutes, go ahead and turn off these nodes. Again, save me some money. Next, I'm going to look in a config directory. And here's where our pipelining work begins. Inside of this config directory, you can see a series of YAML files. And the first thing here I have is replace missing values. There's a load component, which is built into the Azure AI.ml library. And it's going to say, all right, well, my source is the parent directory / feature replace missing files.yaml, this YAML file. If I look at this, this is the structure, a common structure for what a YAML file looks like for Azure Machine Learning. We have our display name, replace missing values. We have the Python friendly name that has underscores. Our version, our type is a command. Our input is a folder. So I'm going to take data from a folder and I'm going to put data into a folder. And this is a common pattern when working with Code First Azure ML. So take data from folder, put data into folder. The code itself will be in the scripts folder. And my environment. This environment says, here is the container image of the type of workspace I want to use for this step. I'm going to use the light GBM 3.3 environment. Basically, this is a Docker container that has a few, or actually a fair number of Python data science libraries pre-installed, including Microsoft's Light GBM classifier. Even if I don't use Light GBM, it's going to have pandas, it'll have NumPy, it'll have quite a few of the standard libraries that I will be using. And the code that I want to run, Python feature replace missing values.py, take my input data and take my output data locations. So let's go into that file, feature replace missing values.py. Inside of here, this is code that is actually going to run inside of a container. If I switch back to the Azure Machine Learning workspace, I have this replace missing values box. Think of this as there is a Docker container that is getting spun up, it is getting instantiated, it is going to execute this code. Well, inside of here, I'm going to use MLflow, I'm going to use NumPy, and argparse, argument parsing. I need to make sure that I have an input data and I have an output data. And if I have both of those, cool, let's keep going. If not, I'll throw out an error. Next, I'm just going to put some information. Here's my input data path, my output data path. We'll print out those lines, and then I'll show the directory of my input data. All of this so far, this is just diagnostics. This is for me to make sure that when I run this code, it works as I expect. Here's where things start getting kind of real. We have our file list. Remember that I sent in a folder. Inside of that folder, I may have one file, I may have 1,000 files. I actually don't know how many I have. Okay, I know that I have one in this folder, but in general, I may not know how many I have. So for each file name in the directory, let's go read that file, and then we're going to open that file as read only and read it as a CSV. Now, I may not know how many files I have, but I need to know what type they are. Are they Parquet files? Are they CSVs? Are they some other format? Could they be Excel files that I need to parse? I need to know the structure because I'm writing code to parse it. Well, we're going to use pandas. We'll read the data as a CSV, and then I'm going to uh, put that in a variable called input data frame. And file list will be a list of data frames. At the end, when I'm done, I'm going to concatenate all these together into one big data frame called DF. I can get away with this because I don't have enormous amounts of data. So now I will replace missing values. Remember, I mentioned police district. I don't have all police districts. So in the event that I don't have a police district, I'm going to fill it with the number 0. And I'll say, replace that in place. Don't give me a new data frame. Just update the one that's currently there. And I will write the result out to CSV as replaced missing features.csv. So that's going to be in my output data folder. So that is what I'm sending out. And the nice part, if you think about this as a pipeline, the output of replace missing values can become the input of the next step in the process. So I have here feature engineering, feature selection, splitting data, training a model, registering a model. These are all individual components that have configuration files that, for the most part, look pretty similar to this. Like if I pop up feature engineering, feature engineering has input data, has output data, calls the feature engineering.py. We're going to use the same environment. This is very similar. If I go over to Azure Machine Learning, we can see it has replaced missing values. It is currently setting up that machine for feature engineering. So this is going as we expect it to. If I look at the Python code for feature engineering, a lot of the structure starts off the same until we get down to about line 40. And here's where I'm setting issued date as a date time. And then that way I can easily grab the year from issued date. So that is my issued year. I'm going to bin my hours into the overnight shift, morning, midday, after work, evening. My idea would be that maybe people who get tickets at certain times of the night are maybe they're less likely to pay, whereas perhaps people who are like midday or after work, they get tickets, they might be more likely to pay. I could be wrong, but it's what we're going to experiment with. And then license plate state, I'm going to say if you're in Illinois, you're in state. If you are in one of these non-US states, you are out of country. And everybody else, you're lumped into a bucket called out of state. For vehicle types, we have passengers, we have trucks, we have temporary tags. Because, hey, people with temp tags, they might be more or less likely to pay their tickets. So we have their vehicle types, and everything else is another. And that's the general idea of what we're doing in each one of these steps. We're putting together some code to work with our data or to work with our model training or to do something else. The other script that I'll look at is train model because that one's a little bit different. We have our training data, we have testing data, and then we have some hyperparameters that we could use for trying out various sets of inputs. I am using a tree-based library to perform my training. If I scroll down a bit, you'll see which tree-based library I'm using, but or you can read it right here. See, oh, it's a gradient boosting classifier. So we're using gradient boosted decision trees out of scikit-learn.ensemble. Come down here, I've got my training data frame. Well, my training data is some percentage of my total set of data. And I do that in the split data section, but I'm kind of skipping over that so that, we're not actually here for 7 hours because seriously, I could talk about this for a while. But we are going to build out a training data set. We're going to uh, process that data. So I've got a function called process data that splits out some of these variables are numerical, per capita income, percent unemployed. Some of these are categorical. So I do, by the way, actually make zip a numeric data point because I'm a monster. But for categorical, time of day, license plate origin, if it's in state, out of country, vehicle type, the community name. These are strings and things where I have a relatively small number of values. My label column, payment is outstanding. So all columns is my numerical columns plus my categorical columns. Both of these are lists. And label column is a list of its own. And then my data frame is all columns. That helps me remove the stuff that might be in here that's not one of the relevant columns for model operation. I'm going to remove any cases where the label column is null. It turns out there are none, but just in case. And then I'm going to drop the label from my predictor, my features, my input variable set, and I'll save my label column as Y. So X is every piece of data that I think may relate to the label. Y is the label itself. Then I'm going to specify the categorical columns as categories and my numerical columns as floats. And that'll process my data. That way it's consistently processed. It's the same shape for training and for testing. When it comes to training the model, I will perform a column transformation. I'm going to do a few things. I'll skip over the specifics of why I'm doing things the way that I am, unless somebody asks a question about it in chat. Otherwise, I'll just note that the code is available. You can grab it and try it out yourself and uh, dig in a little bit further on some of the whys behind it. But the general idea is we're going to train a gradient boosted classifier. We're going to build out a pipeline for our model. So this make pipeline. This is different from an Azure ML pipeline. This is actually kind of a scikit-learn pipeline. It's pipelines all the way down. And then we're going to fit our model. So we're going to say, given this training input data and our training answers, give me a model that using this most closely predicts this. Then we're going to perform predictions. We're going to predict based on test inputs where I don't give them the answer. We have our predicted answers, and I'm going to compare how does our actual test data relate to our predicted test data. And we'll calculate accuracy, F1. We'll calculate precision, recall. We'll calculate the receiver operating characteristic area under the curve score. We'll get all of these things. We're going to write them out into this results dictionary, and I can print the results, and then I can log metrics in ML flow. I can say, here's my accuracy, my F1 macro and micro, precision recall, rock curve. So all of this stuff is in that trained model. And all of these things, I'm loading components up here. And then I'm building a pipeline, a training pipeline that takes step replace missing values is my replace missing values component. And I'm telling it, go look at raw data. Now, where does raw data come from? Raw data is, sorry, here it is. It's my input for this function. So I need to tell it, you're going to go, here's the Chicago parking tickets folder. And that's going to be your starting input data. Well, step replace missing values then becomes the input of the next step, feature engineering. We take the output data of that folder, it becomes the input of feature engineering. Feature engineering's going to then take the output and turn it into the input of feature selection. Splitting data is the output of feature selection. If I pop back over here to Azure Machine Learning, we see the input data into replace missing values, and its output data becomes the input of the next, becomes the input of the next, becomes the input of the next. But split data is a little different because we're going to get training data, we'll get testing data. And you can see I've got two separate outputs that I needed for my trained model. So we're currently training the model, which means we're almost as fast as Azure Machine Learning in terms of my explaining this versus it running it. And I run train model, and train model is going to take a few inputs. It's going to take my split data train and my split data test. I'll take my hyperparameters, 128 leaf nodes, 32 samples per leaf minimum, 12 levels of depth maximum, learning rate of 0.1, 100 estimators. Why these numbers? They felt good to me. I could perform some hyperparameter sweeping operation and try a bunch of different types of outputs and see which ones work best. Here, I came up with numbers that looked reasonably good. And then I'm going to register my model. So I can register the model, saving it in the model registry, taking my model output and the test report, the results that I had from model training. And then I'll return a JSON object that includes those details. The next thing I have is this prepare pipeline job. So I have my cluster name. My cluster name is CPU cluster, is that CPU cluster here. I've got my compute asset, ML client data.get Chicago parking tickets folder, version 1. This is how I tell what is my input data. Because I'll say raw data is a URI folder of this Chicago parking tickets asset. The Chicago parking tickets asset, if I come over to data, I'm going to open that in a new tab. There we go. I've got a few different Chicago parking tickets things in here, but this is the folder. So the folder itself, if I explore it, there is one file in here. It is a text file that's comma separated, and it is the same thing as what I showed you earlier, just in folder form. So I've already created that. I've already uploaded it. Oh, I have already. There we go. Alt tabbed. Bring you back full screen. Come back into VS Code and say, all right, that's my data. I'm going to build a pipeline using that raw data. So in other words, I'm going to call this function that calls all of these things, these component loads. And then I'll set my pipeline job settings. So my default compute is CPU cluster. My default data store is workplace blob store, which is automatically created when you create an Azure Machine Learning workspace. If I have already run this, if you set this thing to false, then Azure Machine Learning would say, oh, you know what? I have results from a recent run with these same parameters. I'm just going to say, you're good, and then let you look at the prior run. If I set it to true, every single time, even if I have the same parameters, it's going to force rerunning. That way, if I'm talking to you folks and if I present this again to somebody else, it'll run it again. And the display name will be train underscore pipeline, which if I come back up here, that's the name right here. It's almost like it all ties together or something. And finally, our actual code. Prepare pipeline job, given the cluster name, and create or update a machine learning job. So take our prepped job from here, and the experiment name will be Chicago parking tickets code first. And that is why I was able to look in jobs in this Chicago parking tickets code first experiment at the train pipeline. If I look at the experiment here, we can see, by the way, that this normally takes about an hour, which means we're not going to get finished with this train pipeline because I am going to hustle through the scoring section. But if I look at a prior edition, a prior run, you'll see we've got all of our different components. And I could do things like I could right click on this component and I could view the log. I could grab some code. I could get some information. Here are some metrics. My accuracy was 75%. My precision 62, recall 32, area under the curve 62. This is not amazing, but it's okay. It's not awful. Maybe. But that's my training. Now the question would be, well, cool, you've trained a model. What next? Well, if I come back to Azure Machine Learning and I go to the model section, what next is I've created Chicago parking tickets code first. You can see I've done this quite a few times because I'm up to version number 14. But I've got my accuracy and other scores as tags. I've created this model. I could deploy the thing and say, you're a real time endpoint now. If I go over to endpoints, I do have a couple of endpoints here already. I've got a Chicago parking tickets. I've got a web service. So I am not going to create another one. I'm going to take advantage of one that I already have. And I'll do that using deploy score. Deploy score is my scoring script. This is how I perform inference against new data. Now, my new data, if I look in this data folder, I've got a couple of files. So here I've got one file that has about 2,200 inputs. I've got another file that has about 390 inputs. So roughly 2,600 or so things to score. And what I'll do is using CS Azure ML in the CPU cluster, if I scroll down, basically this is the same create cluster code that we saw earlier. My endpoint name will be Chicago parking tickets batch. If I have that endpoint, I'm going to get it. If I don't, I'm going to create it. So while I'm doing this, we're going to run deploy score.py. We're going to see how it works. And let's keep talking. Endpoint name is this batch endpoint. I already have it, so we'll reuse it. If I scroll down a bit more, we're going to look for Chicago parking tickets code first. Now, I am specifying the version here because it's all the same code, basically. And I want to, every time I run this and present, I want to use that same model, the first model. It makes me, I've got a lot of good feelings about that particular version of the model. The later ones, I don't know, they may be a little duplicative. My deployment name, batch deployment. If I don't have a deployment name, deployment called CPT batch deployment, then I'm going to create one. And that creation will say, okay, give me Azure ML, scikit-learn 1.0, Ubuntu 2004, Python 3.8. Yeah, you would say, wow, this sounds old. But because I'm using a fairly new version, it's actually not Ubuntu 2004 anymore, and it's not Python 3.8 anymore. It's just the name has stayed the same because uh, it's annoying to see the names change. So, as I recall, this is actually Python 3.10. Model batch deployment. We are going to do batch scoring of the Chicago parking ticket payment status. Is payment outstanding? Our endpoint will be the endpoint that I talked about, Chicago parking tickets batch endpoint. This is batch, by the way. So we have, again, two options. Number one, I can have a REST API. I can send you a post request with data and then get back results. This is really nice if I have onesie, twosie type of scoring. I've got a few records, like 20 records, 30 records that I want to send out and get back some answers. There is some overhead in terms of needing to transit data over the network, needing to work with TCP, needing to work with the uh, protocols for posting commands and sending data back. So this is not going to be microsecond response time. It'll be hundreds of milliseconds response time. But if I have a million records, well, you're not going to get a good response time for a web API or a web hosted API, I should say, because it's not .NET Web API. So you're not going to get a good response time. Instead, what I'd prefer to do is drop those million rows into a file someplace, let Azure Machine Learning read that file, loop through the records, generate results, put that in a file, and then tell me when it's done so that I can check it out later. And that's what we're doing with this batch deployment. So we're going to take a scoring script called scoremodel.py, and we're going to generate a predictions file called predictions.csv. If I go to scoremodel.py, that is right here, and scoremodel.py, you'll notice, actually, I am using the V1 Azure ML.core. It's okay that I'm using V1 for this. I don't have to be incredibly consistent for scoring versus training because I'm not doing a whole lot. All I'm doing is I'm saying, okay, get information about the current run, get information about my workspace, go grab the Chicago parking tickets code first model, and get it from that path, and then load that model because I know I generated that model using scikit-learn. So I'll use sklearn.lowModel. If I generated it as a PyTorch model, I would need to use PyTorch to load the model. Then we're going to take a run with a mini batch. Mini batches are a certain number of files. And if I look at this, if I keep scrolling down, I will be able to see mini batch size is 10. And what that'll say is I have two instances, max concurrency for instance is two. Basically, I'll be able to have different runs of this run function, and each one of them will get up to 10 files. What I'll do is I'll take all of the 10 files, read them as CSVs, and then smoosh them all together, concatenate them all together into one big data frame called data. Then I'm going to call model.predict on that data frame and add to it the outcome payment is outstanding. And then set payment is outstanding equal to predicted payment is outstanding. And that's going to be the result. So I'm going to get back a whole bunch of zeros and ones for payment is outstanding based on the order of the rows in which I receive them. My uh, data path, my data set name is Chicago parking tickets unlabeled. Basically, I took these two files and I uploaded them into the storage account, and I created a new data data set based off of that folder in my storage account, my data store. If I did not do this already, then I'm going to create the data set. And so I'm doing that right here, and then retrieve it. And I have a note here that if you get a by policy error when running this, you have to check that your account is an owner status. So that is important. But next, let's call a batch endpoint. We're going to invoke this batch endpoint. We're going to stream our results, and we will download the file into the local path in an output name of score. So let's check how it's doing because my recollection is this also takes a little while. And you can see it's not done yet. Submitting one run. So if I come over here to jobs and I check out Chicago parking tickets batch, my latest job is cyan cord. And we can see that it is currently performing batch scoring. So what I'll do is I'll let this run. We'll go through the rest of the slides. We'll come back and see if it finishes in time. Okay, building pipelines in code. So we created a Python script runner. We created YAML files. We created Python files for each step in the pipeline. We did some model training. We did some testing against our input data set. We registered that resulting model, and we wrote some code to perform scoring. And that's what that demo is all about. Let's talk briefly about ML ops before we wrap up. Because what I've done is it's a pretty manual process. I ran Python deploy train, Python deploy score.py. In the software engineering world, we have seen a consistent move toward more automation of code operations, of automating testing, automating deployment, automating monitoring operations, etc. In Azure ML, there's also kind of a natural progression where, first off, I can deploy a model via the Azure ML Studio UI. Basically, the designer. The designer experience allows me to push out a model that I could then query against or call REST API commands. Well, from there, you might say, I can do better. I can create notebooks, and then I could actually perform model deployment. All of the code or a lot of the code that we worked through, I could create a notebook to generate those outputs. That works well if it's a one-time thing or if I'm just trying stuff out. But I could then do model deployment via AZCLI, which ultimately is what I did when I was running these. If we look at, this output here, what we're actually doing with this scoring script ultimately is we're calling the Azure CLI and it's performing certain operations behind the scenes for me. So like here, invoke batch endpoint, that's really running the AZ CLI behind the scenes. And what's neat about that is, well, if I can run that manually, a computer can run that automatically. And that's where we get into model continuous integration and continuous deployment using tools like Azure DevOps or GitHub Actions. Now, that is not going to be what we'll talk about today. I've got a whole talk dedicated to that topic. There's a lot that I can talk about in there. But we get to this notion of machine learning operations. So this is built off of many of the principles of DevOps, but we've tuned it to a world where data and artifacts and models are just as important as the code itself. And so the biggest problem here isn't necessarily deployment of code. It's automated retraining and redeploying of models as they get old, as they get outdated, as they're no longer as accurate as before. And a proper treatment of ML ops does take an entire session. I know because I've written that session. So before we wrap things up, let me go back to here and we can see, oh, hey, batch scoring is done. So that's a good sign. And I could come back to here and I can see it completed the processing run. It downloaded the artifact. So I should have a file called predictions.csv that has my inputs. And then if I scroll right, I can see, ooh, we predict that this person here who got a ticket in Archer Heights uh, in 2003 probably never paid that ticket. And so I could, take these. I could then understand how closely they actually relate to reality. I could go back and dig up the information for each one of these tickets and see if my predictions were right. But through all of this, all of the training happened through code. All of the scoring happened through code. We interacted with the Azure Machine Learning Studio. We can use the interface here. We could use this UI to understand what is going on. And I could still look at like this training pipeline here and see that, yeah, it's still running. It's going to perform training for a little while. And that's okay because eventually it'll finish. It'll register version 15 of that model and I'll carry on. And if I were doing this in appropriate order, like if this was the first time I ran this, I would need to wait for the training to finish, wait for the registration, and then I would call scoring. But because I have a copy of this is like one of those cooking shows where I've already got the finished version in the oven. I could pull out the finished version and say, "Oh, look, here's our scored model." So with that, Over the course of the last, almost hour and a half, we've looked at a variety of ways to take Azure Machine Learning beyond just drag and drop user interface and turn it into code first programming, ML pipelines. I've talked a bit about ML flow. I've talked about how it ties in with Azure Machine Learning. And we saw at a really high level that ML ops can help us push out changes more efficiently. If you want to learn more, you can check out csmore.info/on/aml in depth. And I'll copy this into private chat so that maybe Adriano could paste it into the comments here. If you want to get the next talk in the series, if you do want to learn more about ML ops, the csmore.info/on/ML ops is available. Also, one nice thing about these is I have also turned these. So I have a recording of this talk, but I also have a playlist for an Azure Machine Learning YouTube series. It's something like 13 or 14 videos that takes you through the entire 3 talk series. So you can check that out as well. And I'll copy the link and also uh, make that available if you are intrigued, interested, wish to learn more. So, with that, if you do have follow up questions, I am happy to take any questions right now. Or if you want to follow up with me afterwards, you can send me an email or you can reach me on X. And with that, everybody, if I see anything in chat, we'll be happy to talk about it. Otherwise, hope you enjoyed it and have a wonderful rest of your day.
All right. Great presentation here by Kevin. Thank you very much, Kevin. I am just about finishing entering your references here into the chat. And what I'm going to do too, I'll update the description in just a second, folks. And so here we have the links. I have your YouTube, the videos, and on the references, documents, docs. And then we also have docs for ML ops docs. All right. All right, folks. So, all right, folks. Got a question? Do not hesitate. Enter your question in the live chat right now so we can get follow up here with Kevin. Now, if you're unable to do so right now, use the comment section below and we will follow up. We'll forward the question to Kevin, follow up here regarding the answer. Now, as Kevin mentioned, there was a lot of information today. He took definitely to the next level here by going beyond the traditional Azure Machine Learning designer that you generally see, which is the drag and drop interface, to a code first approach, or Python is the lingua franca here, the primary language in the use. And you saw, as he outlined, right, the use of VS Code, use of ML flow to try and fit the feature engineering selection, along with the standard split data and tests. You talked about scikit-learn, and even walk us through a gradient booster model as well, in addition to a lot more things that he also mentioned here. So let's take a look. Let's take a look if we have any additional questions here. I don't see a question right now. I do see that there are people watching, but I don't see a question here. Anyway, so with that,
send them all into silence.
Yes, a lot of people are probably shocked to hear like there was a lot of information coming through. So with that, let's thank you very much, Kevin. for the Beyond the Basics with Azure Machine Learning session. Definitely very rich presentation here with a lot of information. I know, folks, feel free to come back, review the session. I know that you may have to take bite by bite because there is, it's like a fire hose right now of all that information there. And now, as it relates to future presentations, we will also, the Microsoft Data and the AI user South Florida user group will continue the team by having the machine learning and AI presentations in the pipeline. We have bringing it up to you in the next couple of months. We will have build your RAG solution using Azure and OpenAI. And we will have another one too that will be based on ML prompt flow, the Copilot scheme. So we're really engaged to bring to the community and providing and exposing whether you are a data professional and or a software professional to learn about each other's job there as these technologies, AI, ML, and data are all intermingled, but also bringing new and exciting technologies to make your journey and exposure simpler there so you can ramp up faster. Now, with that, let me take another look to see if there is any more questions or comments here in the section. Now I don't see anything new here. So folks, thank you very much. Really appreciate making the time to be here with us. Remember to share, like, and subscribe, and remember to click the bell as well so you are notified when new videos and presentations are coming. And again, Kevin, just hang on a little bit more. And in the meantime, folks, thank you. Have a great day. And I will see you on the next presentation coming on October. Do well.
Thank you, everybody.